Hello, good morning. I'm Lokman. I have been working in National Meteorology Institute of Turkey at Electrochemical Laboratory, and today I will try to explain voltammetric technique and the fabricated sensors and biosensors produced by us. First, I will briefly explain the technique we used. Then I will try to explain the electrochemical biosensors and sensors that we produced for diagnostic of COVID-19 and the technical SARS-CoV-2 antibodies and some toxic metals or organic inorganic compounds in synthetic and real samples. At first, voltammetry is based on polarography, but over time, voltammetry developed more than polarography. Then the technique is named voltammetry. The main difference between these terms is that mercury drop electrodes are used in polarography and the others are used in voltammetry. The polarography, which is fundamental of voltammetry, was invented by Jaroslav Herovsky. And on the left, you see the first polarograph made by Jaroslav Herovsky. And on the right, it is the image of Nobel Prize ceremony in 1959. And Herovsky took the Nobel Prize in the field of chemistry. Voltammetry briefly is a combination of three words: voltage, ampere, and metry. That means the voltage is applied and the current is measured briefly. More comprehensively, the potential is applied between the working electrode and reference electrode, and the current passed through the working electrode and counter electrode is measured in the meantime. So we call this technique voltammetry with double M, not one M. After a brief introduction to voltammetry, I would like to give a brief overview of SARS-CoV-2, which is the causative virus of coronavirus disease, and it is the biological material that we are most interested in for its determination, which caused great destruction by appearing in 2019. Like other coronaviruses, SARS-CoV-2 has four structural proteins: spike proteins, nucleocapsid, membrane, and envelope proteins. And nucleocapsid protein holds the RNA genome here, and the other proteins together create the viral envelope. And here the sham illustrates the detection methods for SARS-CoV-2 and the related other segments of viruses or bacteria, etc., biological materials, which they are, the methods are lateral flow immunoassay method. ELISA, real-time PCR, is well known due to the COVID-19, and nanopore target sequencing and biosensors. As it's well known, since spike proteins are the outermost, their determination is easy, but they are the most mutated proteins. And although the mutation rate in nucleocapsid proteins is much less, the virus capsid must be exceeded in their determination. A detergent must be used for this application, and real-time PCR uses a similar approach for RNA determination. But in biosensors, almost all protein types can be determined with the proper biosensing platform design. Due to this situation, in recent times, there's a great tendency to voltammetric methods due to the high sensitivity, selectivity, being fast, simple, and portable. So sorry. So what we are doing in this field, we develop electrochemical sensors and biosensors for the determination of some analytes using this technique. You can see some of our studies on the slide, and this is the discriminative wild type and Omicron variant detection of SARS-CoV-2, and this one based on the optical and electrochemical detection of copper and mercury ions, and this one based on the detection of well-known antioxidant quercetin in some fruits and vegetables, and I will explain them in further slides. Our first study is the spike protein detection of SARS-CoV-2 with a developed platform in real samples. And I would like to state that our study was published in Biosensors and Bioelectronics, which is the second rank in the world as a site score and impact factor in the field of electrochemistry. To prepare the biosensing platform, first glassy carbon electrode was polished and paraffin oxide was deposited on the surface, and the obtained surface was activated by EDC and NHS chemicals to ease the antibody immobilization on the surface. Thereafter, after the immobilization of antibody to the surface, then the free sides of the electrode were blocked with bovine serum albumin. And I'm so sorry. The developed sensor was used to detect the SARS-CoV-2 spike antigen proteins in the for the diagnosis of COVID-19. Clinical samples were tested by using the described methods here, biosensing platform, real-time PCR, and rapid antigen test here to examine the efficiency of the disposable biosensor. And to this end, more than 90% specificity and sensitivity were obtained for negative and positive samples. Also, it is crucial to indicate that we obtained false negative results with real-time PCR at 100 copy per milliliter, but we achieved to take a response of 170 nanoampere current increase with the developed biosensing platform. And that means our biosensing platform is more sensitive than the real-time PCR. In addition, we produced a potentiostat galvanostat instrument with a compatible software, and we performed all real sample applications with this instrument. You can see the sensor supporting material. We obtained this item as a commercial one, drop sense, I think, and this is the connection cable. And this contains 3 electrodes. Here, the middle one, circle one, is the carbon ink working electrode, and this one is the counter electrode. It's also made of carbon, and this one silver chloride electrode. And we modify this electrode with the proper chemicals, as I mentioned on previous slides, onto the working electrode side. And we after that we drop the saliva or oropharyngeal swab samples to this circle, and we measure the signal. You see the image of the produced device, sensor, and software here. We embedded the potential scanning modes into the software of the device, as you see here: cyclic voltammetry, differential pulse voltammetry, and square wave voltammetry. And also in this year, we have a plan to integrate different potential scanning modes or current scanning modes like linear sweep voltammetry, corona potentiometry, and corona amperometry into the software. Here you can see the current potential curve of the ADC card used in the instrument compared to the age-length digital multimeter. And here it's possible to say that the results are at an acceptable level. And finally, you can see the superior characteristics of the developed platform, biosensing platform, with a compatible instrument here, such as high sensitivity, high selectivity, and accuracy, and low cost also, and the short analysis time compared to the real-time PCR. And due to the time limit, I will very briefly explain our other studies apart from the previous one. Our second study is the antibody detection of SARS-CoV-2 spike protein in saliva and oropharyngeal swab samples. And systemic gold-based electrode was produced, and the interference effects on enzymes, compounds, and ions that could be found in saliva were investigated, and the results showed that the developed method is quite selective. The other one, SARS-CoV-2 spike antibody detection method in real samples with satisfactory results based on hydrogen bonding, markup ethanol gold-based electrode. One of the most important aspects of this article is the comparison of the developed sensor here with the lateral flow immunoassay kits currently available in the market. As you see from the figure, it was crucial to indicate that the lateral flow immunoassay method responded as a faint line here, 100 at 100 nanogram per milliliter of the SARS-CoV-2 spike antibody, and gave a negative response at lower concentrations, 1 and 10 nanogram per milliliter. And the results clearly depicted that the developed biosensor was billion times more sensitive than the lateral flow method. And since patient individuals may have different virus levels and therefore different antibody levels, it was concluded that the developed method could be successfully used after the onset of symptoms and early diagnosis of COVID-19. Our fourth study is based on the optical and electrochemical detection of SARS-CoV-2 spike antigen in synthetic samples. And here we produce gold nanoparticles with strata reduction method, and we immobilize the markup of nucleic acid and antibody onto the gold nanoparticle surface, and we detect the antigen protein with Voltammetric instrument and also UV visible spectroscopy with good results. This is the other approach to detect the SARS-CoV-2 spike antibodies in synthetic and real samples approved by real-time PCR and rapid antigen test kits. Here, the most important phenomena in this study is the combination of linkers here with the SARS-CoV-2 antigen to shorten a period to produce the biosensing platform. It's about 2 hours. We have 2 hours before the preparation of the biosensing platform. And sustain-based cold electrodes we produce for the diagnosis of COVID-19 in real samples. And we have good results in terms of specificity and sensitivity in this study. Also, and final platform for COVID-19 diagnosis, this study includes a platform developed for the detection of nucleocapsid proteins instead of spike ones. And the crucial feature of this platform is that it enables differentiation of the wild type, I mean the first part of the SARS-CoV-2 virus, and the Omicron variant of the SARS-CoV-2 nucleocapsid protein with a single platform. I mean, we can determine the original virus or the Omicron variant with a single platform on the same platform. And this slide is very important for us. We really like the fact that the researchers from MIT and who we don't know mentioned our team as one of the most active groups in their article about the topic of COVID-19 diagnosis. Our latest platform was developed for the determination of cortisol in artificial bodily fluids with the similar approach. And very good results were obtained with this platform. As for the electrochemical sensors, our first example involves electropolymerization of the 3 chemicals, as you see here, on a On a pencil lead, as you know, it's graphite. The important feature of this study here that we use tombow leads and a pencil body as a supporting surface and as a working electrode, because the tradition the method is quite cheap, because traditional glass carbon electrode is about €200, but one graphite lead is about €0.05. And we use this sensor to detect molybdenum in water and food supplements successfully. And similarly, we used polymer and carbon nanotube modified electrodes for determining the boron in dried fruits and nuts here. And also we developed a method for determining carbonate or bicarbonate ions in real samples with a bare pencil graphite electrode. And we used azomethyl H as a complex region. And we performed various real sample analysis with this sensor, and we compared our method with the potentiometric cheapness also. And also we developed a method for determining ferric ions in real samples with pencil graphite electrode, and we used quercetin as a complexing reagent here. And we characterized the electrochemical reactions occurred at the onto the electrode surface here with some techniques: UV visible spectroscopy, NMR spectroscopy, voltammetry, and cyclic voltammetry, etc. And this is another example of electropolymerized pencil graphite produced for the determination of antioxidant quercetin in some fruits and vegetables also. And the proposed method and UV visible spectrophotometry were used to detect the quercetin ingredient in real samples, and the compatible results were obtained with both methods. And our last study is based on the polymer film modified electrode, again for determining toxic compound named hydrazine in water samples with satisfactory results. Because I would like you to see our many different studies in this field, I have to go fast this way, and I'm sorry for this. I hope it has been useful. My presentation finished here. Thank you for your attention.